Hi, everybody. Um, I just first want to say that I hope everyone's doing okay. I hope that my little modules are clear enough to understand. I hope everybody is, staying safe and that your families are all right. Um, all right, so I'm just gonna get started. So this next set of modules is going to be about how the concentration of a reactant changes over time in a chemical reaction. Okay, so far we've covered, how to determine a rate law from initial rates. Okay, I also that I did before spring break, and I posted two review sets of notes on that in case you missed it. Then I did five sort of modules on collision theory, which explains about the different things that happen in a chemical reaction, and it talks a lot about activation energy. And now I'm going to do this new set of modules, which focuses on how exactly the concentration of reactants and products changes with time. Like, what is the exact dependence of that concentration on time? And so you might want to know, well, why do I care about this? Why is this important? So I thought I would give you a few examples of why this might be important. One of them would be like for example, and for me, about 10 years ago, I had to have my thyroid removed because I had thyroid cancer. And so after they take out your thyroid, they treat you with radioactive iodine, which kills off any tiny little cells that might have remained. And so the iodine 131, which is in your body, which is, giving off radiation to kill these cancer cells, what you'd like to know is, well, when is it going to be safe for me to, be with my child or sleep in the bed with my husband? One day I brought home a Geiger counter from the lab and put it next to me in the bed, and it was going, and Steve said, yeah, maybe I should sleep in the other room for another night. So anyway, but when can you actually be sure that there was no longer a harmful level of that iodine 131? Another thing you might want to know is if there was a toxin that was introduced in drinking water, how long before that toxin gets down to a safe level. That's something that you'd really like to know. How long, well, anyway, so that would be a much more complex kind of situation because the toxin could do many different things in the water, and there are probably many different rate processes that could cause that toxin level to go down. But the radioactive decay one is really simple because radioactive decay is what we call first order. You know about first order from what I covered earlier. And so we're going to be able to, in this course, very, an introductory type of course, we're only going to talk about how concentration changes with time when the reaction is first order. We're not going to be able to do anything more complicated than that. Okay, so what I'm going to do is go over to OneNote. All right, so here I am in OneNote. And so what I'm going to be doing, get some lines here, is I'm going to be talking about, for first order reactions only, how does concentration change with time? And I'm really going to be talking about the concentration of the reactant. I say the reactant because if you remember, this is what first order is. The rate law for a first order reaction is that the rate is simply proportional to the concentration of reactant. So it's really like you have A, the reactant A, going and forming products. Okay? So that's what we're going to be looking at here. So only first order. So this is first order because this is the 1 power. Okay? So anyway, what I want to talk about is how you will go from reaction rate to concentration changes over time. So in other words, how will we be able to use K and the time elapsed or the time passed to calculate the change in concentration. So before I start talking about reaction rates, I thought I would do kind of an analogy. Okay, and the analogy that I'm going to work with is, well, first of all, a rate is like a speed, right? You could say the rate that your car is moving, or you could say the speed that your car is moving. So a reaction rate is equal to the change in concentration divided by the elapsed time. We talked about that. If we're talking about speed, like the speed that a car is moving or the speed that you're walking, that's like this change in distance. Oops, I don't know how to spell again. Over the change in time. So reaction rate and speed are both changes in something over the change in time. Okay, so the question is, let's think about in terms of the car and the speed. Okay, so if you know the speed and you know the time that passed, so if you know how fast the car is going, can you calculate the distance that's traveled? Can you find the distance traveled? Okay, so how would you do that if you could? So I would say that yes, you can do this. Okay, that's easy if the speed is constant. So this is easy if the speed is constant. Okay, so how would you do it if the speed was constant? Well, speed equals distance over the change in time. Okay, so if you take the speed and you multiply it by the change in time, you'll get the distance traveled. So in other words, if you're going at 60 miles an hour and you multiply that by 2 hours, not worrying about sig figs here, that's going to be 120 miles, right? You can even use dimensional analysis there. Okay, so can you do the same thing or a similar thing for reaction rates? In other words, can you take, since the rate is the change in concentration over time, right? Can you take the rate and multiply by the change in time to get the change in concentration? Can you do this? What's the answer to that question? All right, so think about it. The reason you can't do this, I would say no, you can't. And I hope that you can guess the answer. The reason is because chemical reaction rates are never constant. You can't do this. The rate of a reaction is never constant. Why is it never constant? Well, because the rate always depends on the concentration of reactant, and the concentration of reactant is always changing as that reactant gets used up. Okay, so if you remember back from the very first day where we talked about a graph of concentration of reactants with time, remember it looks kind of like this. Okay, so at the beginning, you have a very big slope, like you have a large change in concentration over change in time. So this is a large slope. So the slope, remember, is the rate of reaction. And here, now you have a very small change in concentration with time, which is the slope. So you have a smaller rate. So as remember, I said that reactions start fast and they end slow. Okay. So we can't use this idea that you can just multiply the change in time by the concentration, because if you rearrange this equation, multiply the change in time by the rate to get the change in concentration. You can't do this because this is not constant. And that's a big pain, all right? So we really can't use that simple method. So what are we going to do? There's a problem, okay? So in order to come up with an equation, so what we really want here is an equation that relates concentration of reactants. And in this case, like I said, we're doing first order, so there is really only one reactant. Relates concentration of reactant to time. So this is what we want, an equation that relates concentration of reactant to time. But the thing is that in order to get this, we need to use calculus. And I know that some of you have had calculus or maybe taking calculus now. But I want to tell you what calculus was invented for. So calculus is a branch of mathematics that was actually literally invented to handle rates that change with time. So it was invented to handle, in a way, rates that change over time. And chemical reactions definitely have rates that change over time. They start fast and they end up slow. Okay, so for simple reactions, so in other words, simple rate laws. So for example, that's what I really mean was for simple rate laws. For example, if the rate, like I said, for first order is like that, that's first order. Or it could work for a second order if it looks like this, proportional to the square of reactants, that's second order in A. Okay, so for these simple reactions, calculus allows us to get an equation like this. That means an equation that relates concentration to time. Okay. Yeah. All right, great. So how do we do this? So what I'm going to do is show you how to do this. All right. So now obviously I know that many of you have never taken calculus and never will take calculus. But if we have a reaction A to products, and we know that the rate is first order, so this would be the negative of the change in concentration of A to the change in time, and this is the rate of change of A with time is proportional to the concentration of A to the 1 power. Okay, so that's first order. Then we can use calculus to solve this equation now. So I'm going to solve the equation using calculus, and those of you who understand some calculus, that's great. If you don't, that's fine. We're just going to get to the equation, and then I'm going to show you how to use that equation. So those of you who've had calculus, here it is. All right, so now when you do calculus,